Welcome to our fifth video in the Structured Process Improvement Program. This orientation video is going to focus on reading and interpreting process analytics. As we've seen so far, measurement systems is an important component in understanding and establishing strong standardized work processes. So how do we read and interpret those measurement systems? And that capability is exactly what we're going to talk about in this video. So we have three topics we're going to discuss. What is the idea behind statistical thinking? Many of us have been afraid of statistics, and so we ignore statistics and have avoided it. I was this way for a long period of time in my own academic career until I had to take a course that was required. And when I did, I found that it wasn't all that bad. But I also realized that the academic approach was not the best suited to me. So we're going to take a different approach, a broader approach, where we're talking about how do we read and interpret the graphical output rather than worrying about mathematical proofs and the numerical calculations. The second question is, what data analysis can we use to establish a baseline of performance? This enables us to compare before versus after changes in a process and see what degree of improvement have we actually made in critical performance indicators. And finally, we'll take a look at how do we interpret this data analysis capability. What does it tell us about the real world performance? And more importantly, where we can go to make improvements. So let's take a look at this at a beginning quotation. There are two things that I tell people who are studying advanced analytics that are important. One is skepticism and the other is curiosity. We have to develop skepticism about the data that we observe in our process. Is it actually meaningful, or are there errors and biases in the data and the way it's been collected? The second thing we have to have is curiosity. We have to understand, where did the data come from? What does it mean? What are the implications? What could have gone wrong in the data? And if there's something that is not intuitive about the data, then we need to understand why is that, if you will, not following the expected pattern of performance. Now, Lars Nyberg and Mark Hurd, in their book, The Value Factor, made this comment. They said the key to any business puzzle is to look outside the standard reporting process. And the standard reporting process is basically using standard cost accounting and financial metrics, and to spot the unusual trends. So those few variation observations in the measures that are not where the majority of the data is, those are the things that we see, they're different. There's something unusual in the pattern, and we should try to find out why is that happening. Now, statistical thinking grew out of a series of studies done in the 1990s by the statistical community in America. And it was summarized in these works here by Roger Hurrell and Ron Snee. And basically, it's a learning process. We use it for acting and changing processes based on three principles. The first principle is that all work occurs in a system of interconnected processes. That shouldn't be a surprise. We've been talking about that in terms of process thinking. Variation exists in all processes, and we can use data to learn about the processes, provided we've taken the measurements. Understanding and reducing variation are the best ways to improve operational and business performance. So we have to understand the process and find out what can be done to get rid of the unusual effects that create the variation, and that helps us to improve the business and get better results financially and operationally. So here's an example. This is from a 2007 data set of a call center. What we see here are the average call centers, or call center performance, for each of 7 days from 2007. And we see that the average answer time was 3 to 9 minutes throughout the week. And we see that that's not really acceptable and improvement is needed. So when we take a look at this, we start seeing that what can we do? Well, the first answer of the team was, let's send this information to management. It's our measurement system. And then they can tell us what we should do differently. And management said, scratching their head, I don't know what to do with that. It doesn't tell me anything. So what could they have done differently? Well, they could change the way they present the data and then do it in a way that summarizes the data more effectively than just showing average performance data. So to do this, we're going to introduce a new graphical concept. It's called the box and whiskers plot, or a box plot. And so what we see here is that the average here is represented by the circle with the plus sign in the middle. It looks a little bit like a bomb site, if you will, from a World War II bomber movie. And then the box represents 50% of the middle data. And the line that's in the middle of the box is the median, or the 50th percentile. So half the data is above that line, half the data is below that line. And the green box then is the center quartile, or the quartile above and below the median. So that's the center 50% of the data. So above there, that fixed line is 25% variation above the box, and the line below is 25% variation below the box. The asterisk at the top represents an outlier. It's basically something that is not continuously part of the distribution data below it. And so it's just turned on to say this is somehow different from the data that we have below it. Now, if we use this as a way to plot that week's worth of performance in the call center, we get this result. And we start seeing it's very different than what we saw when we just looked at the averages. As a matter of fact, what we see is, wow, look at these. The days are relatively the same, but not good performance. And Friday is particularly bad. So if we use these averages alone, we create optimism. We think that the process is much better than the experience of the customers. And that's going to distort our business decisions as well as the way we interpret how the customers think about us. So we take a look at Friday, we see that the average was 4 minutes call answer time. The shortest was 5 seconds, but the longest was 1 hour and 10 minutes for somebody waiting to have the call answered. Now, as we look at all of this data, we see it falls into 2 categories. There is the systematic result, or the systemic result. That's the box and whiskers. And so that is performance that fits natural process variation. We can actually identify it and treat it numerically because we look at that with the quartile system. However, the long tails, these are the unusual variations. This is the asterisk, or the outliers, as the statisticians call them. These represent some sort of unusual performance that is outside that statistical distribution we had before. And so we see, that's not predictable using the same type of tools and methods we have for predicting the box and whiskers plots. So if I take a look at this data now, and I say, here is the actual call center data, the number of seconds for all calls happening on that Friday. And so here are the calls in seconds, and we see that the longest time was 23, 330, 381. That was the sequence call. That was the one that came in that was the end of the day. But the top one came in at the very top of that peak is a red dot. Now what we see here is on this chart is 3 basically shifts of data. So from 1 to about 1200 is the night shifts. That's from midnight till 8 o'clock in the morning. And then from 1200 to approximately 17,000 is the day shift. And then the night shift came on from 17,000 to 23,000. And we see each of these has different patterns. And so they're saying there is significant variation shift to shift. So that's interesting, first of all. Not all call center performance is the same. It's not all uniformly distributed. And there's something happening differently in the first shift, the second shift, and the third shift. And so we can start asking and conducting an inquiry to find out what's actually going on. So as we're looking at this, another way of seeing that exact same data is to draw it as a probability plot. And here what we see is the same data referenced to probability of performance using a normal distribution. Now, there's no way this data is normally distributed. And this is what we see. So if I take a look here, I see one distribution is going right at the 0 and is going pretty much straight up. Now, the blue lines there represent a normal distribution. And that's actually the 95% confidence interval around if this was all normal data, we would expect it to be there. But what we see is that this first distribution is normal, but it's got a different slope. And so we see that there's something happening there that is actually one pattern of behavior. Now, somewhere around 60, 65%, we see a second pattern of behavior emerging. And maybe there's a third pattern of behavior in there. But what we see is the slope has changed. There's an inflection point, and by going off at this angle, we see that there is a change in the behavior of the data. So something else is happening, and that is also almost normal, and it represents a majority of customer experience. So there's basically some 30% of the data that's going out there, and it's not the performance we'd like to see. So there may be a third long tail distribution that's above 3,000, and that's 1% of the data. And so we see, something else may be happening there too. So we start getting some understanding that the data is not performing the way we'd like it to. Now, Schuchart established this idea of control within limits that we talked about in the last module. And he said the state of control is where we can go without changing something significant. So we're not putting in new materials, new designs, or new operators or training people. We're doing just basically the same thing. And we should expect the same results. So if we do things in the same way, we should see results that are similar. And so the problem is that eliminating noise and enhancing signal is what we have to do. But the weakness is that the noise is still in the signal when we use the summarized data that's in the X-bar R chart, which is what Schuchart created. He did create something called an individuals chart, but it was never used because the measurement noise was too significant in the 1920s and 1930s. And it was only until we got computers involved and extensively used after networking systems were created in 1987 with Ethernet that we could actually start getting good results of the measured process data. So what do we see? Well, here is this control chart. We see that this is the historical view. And if we take a look at this, we see that there's data between the upper and lower control limits. And then we see the average. So basically, we see there's two sorts of distributions happening. One below the data lines, this upper control limit, and one above it. The one above it is excessive variation. It's why we would study this, because that is not a process that's operating in control. It's not predictable. The lower one is predictable within limits. And if we can reduce the limits, we can control it better. So the idea is that this latest observation, that's called what I call the Bayesian moment. It's where the probability of A given B. So the probability of the future state given the past states is what we would be expecting to see for the future. And that's why we change from historical views of data into probability plots of the future. So to characterize this transition from historical data to future data, we have to change from the data distribution analysis capability to the probability plots. Now, one of the problems with the data distributions is that sometimes we get so caught up in looking at averages, we don't really understand what's going on. So this is an example of performance from a company. The executive in the company that I knew came to me and said, Greg, we're forecasting in our MRP 1,400 units a month of this, but we never sell more than 700. Can you tell me what's going on? You know, why is our forecast so far off? And the answer is, when we take a look at this, that they had 71 months of data, and there was a significant downward trend across there. And as a matter of fact, there was a shift from the initial sales condition to the current sales condition. So yes, he's right about the 700 a month. He's right about the forecast of 1,400 a month. But the problem is that the forecast was never updated to the current sales situation. And so they were always forecasting, including old data in the process. So as we take a look at this, some of these changes they planned, and those were the upper side, those were all advertising campaigns. And on the lower side, the unplanned ones were the changes in the marketplace and the growing obsolescence of the particular product. So what we start seeing is there's two types of process variation. We can see variation within a rational subgroup. So basically, variation within a rational subgroup is where we start seeing something happening. So in this case, what was happening was the demand change for that particular product. And so if we take a look at variation across rational subgroups, we can start seeing, well, what happened? Did the demand switch to another product? Well, yes, it did. It switched to a more modern product. That one was going up. This one was going down, but nobody did a cross correlation. So the special cause variation, if you will, can be assigned to a cause, obsolescence of the product. Common cause variation is a variation that's changing only randomly. But here we saw this at the front end of that process when it had a series of advertising campaigns that were more or less successful. And we started seeing this sawtooth type of pattern going up and down, and that was telling us that those were common cause variations, the various effectiveness of a spot campaign versus no campaign. So those were all email blasts, if you will, and the email blast has a limited type of horizon for getting attention to people and getting them to respond. So common variation is changing only randomly. Special cause changes because we did something. So if I take a look at this data and I say here is order turnaround time, and I want to interpret this, well, what I see is order turnaround time. The type of measure, goodness, is a smaller number. Smaller is better. We get the product to the customer faster. Longer is not better. I mean, if I take bigger as an example here, bigger is worse because it means delays on delivery to the customer. And so Bob, the best of the best, is this lower distribution where we see the green circle. The red is the worst of the worst, or the long-term variation in the process that is not what the customers are expecting. So as we start taking a look at this, we can use the data to interpret the performance for the particular metric and understand the impact of not just the averages, but also the distribution and the way they change as patterns over time. So here's a team discussion for you. What data do you have available for analysis using these types of statistical methods? What type of information would you have maybe about the defects in the products, or the cycle time of the process, or the delivery performance to the customers? How do data observations align with known issues of problems that are having negative performance on customer perception? And where would data analysis help you to understand your process performance in a better way? So those are all interesting questions to take a look at, and please have a nice discussion about them. Thank you.